Okay, good afternoon, everyone. Let's get started. So first of all, be careful. Our deadline of project selection and also homework 1 is coming. So again, if you haven't started, please start right now. Won't be too much time. In my office hour, I talked to a few students about homework 1 problems. Looks like they're doing well. So if you're in a good shape about homework 1, so that's good. Right? If you're however, if you haven't done any problems, please start right now. Don't try to rush, last a few hours. Okay. Okay, today we're going to talk about generalized linear models, right? So a type of widely used probabilistic models in probabilistic learning. Right? So before we talk about the details, we can take a look what we have discussed so far. And so we build up our discussion in the bottom to the up fashion, right? So at the bottom, we talk about very basic stuff like matrix vector, derivatives, MLE, MEP, convex conjugate, and important concepts in information theory. Then we review the definition of probability space, what is random variable, what is the expectation variance, their general properties, right? We introduce an important family of distributions, which is called exponential family. We'll talk about important assumptions in Bayesian modeling called extendability, which is which gives some theoretical results called Bayesian theory, right? And then based upon that, we further talk about commonly used distributions, right? Bernoulli, binomial, beta distribution, Euclid distribution, categorical distribution, Gaussian gamma, V-chart, student T, and so on, right? I'll talk about the conjugate parts, we'll talk about uninformative parts. So as we emphasized before, this is like if you want to design a probabilistic model, right? It's like building something, like building a house, right? You need to prepare some basic units. Like you have to prepare bricks, you have to prepare steels, you have to prepare frames, right? And once all these things are ready, you can use them to construct whatever models you have. Of course, the choice of those different units depends on your particular problem and your own assumption, your own understanding about this problem. Right? So now we kind of like cover all the necessary ingredients or basic units for the probabilistic learning. So in the subsequent discussions throughout this semester, we're going to introduce different types of probabilistic models, which include generalized linear models. Then we'll move to the so-called graphical models. So you see that we're going to use graphical language to describe the structure of models and also review what kind of conditional independent structure reflected in the graphical models, right? And then we'll talk about the popular Bayesian neural networks, right? Which can be viewed as a Bayesian generalization of neural networks. And we'll talk about Gaussian processes, which many of you, if you're not from CS domain, you're doing research in your own area, you might have used this before, right? We're gonna introduce Gaussian processes in the probabilistic learning framework. Right? So these are this will be discussed. All those will be discussed in the modeling framework, right? But only talking about modeling is not enough, right? Because we have a model, right? We have designed a model, and we got data, right? So we want to use the model to fit data, and then to estimate whatever things we're interested. For example, we want to estimate some hidden properties of data, we want to make some predictions, right? So in a Bayesian framework, this results to a posterior estimation, right? So then the question is, how do we efficiently compute the posterior distributions, right? As we discussed before, in most cases, unfortunately, the posterior distribution is infeasible to compute, meaning that you cannot directly apply Bayes' rule
to get exact posterior, you always have to resort to some approximation techniques. So we're going to talk about several commonly used approximate inference framework, which includes Markov chain Monte Carlo sampling, variational inference, message passing, which is mainly based upon the graphic models, and Laplace approximation. So this is our plan. So in our next stage, we're gonna discuss several important and widely used probabilistic models and frameworks, and then we switch to efficient posterior estimation algorithms, right? So it's not like, okay, we're gonna introduce like 10 models and then introduce 10 inference algorithms. Actually, this modeling and inference are kind of interleaving. Like we're gonna talk about these models and we'll talk about the inference techniques. We'll talk about next model, we'll talk about inference techniques, right? So we use some like typical models as an example to illustrate particular type of inference algorithms, which we'll believe that will be easier to accept. And also, once you know that model, and then we talk about inference algorithm, you can directly implement and try it. Does it make sense? Okay. So our first topic includes a large family of models, which are called generalized linear models. Right? Unfortunately, not unfortunately. So don't get confused. Right? This is not talk about simple linear models. So we're going to talk about the general family of models, which includes some kind of linear structure. That doesn't mean like, okay, this model can only estimate or assume linear relationships between the features or between the features and predictions. Instead, you can use that to construct very powerful nonlinear models. So we're going to talk about linear models for regression, linear models for classifications. Again, I would emphasize linear means that just some linear structure inside model. Doesn't mean that it models linear relationship. And then we're going to generalize those linear models in an exponential family. We'll talk about how in exponential family we're gonna how we can estimate the model parameters. So, so first talk about linear models for regression. Right? So we're gonna introduce linear structure with some basis functions. Right? So basis functions can be viewed as some kind of transformation of original features. Right? If you can introduce some nonlinear basis functions, meaning that you have incorporated a set of nonlinear transformation and do a linear combination of them. So overall, your model will be nonlinear. But in the higher level, in the last level, you're gonna have some linear structure. And then we're gonna talk about overfeeding and regularization, right? So if you have taken my machine learning class before, we give some general definition of overfitting, but here we're going to talk about overfitting behavior from the probabilistic model perspective, which might be different from what I have discussed in machine learning class. So then we'll talk about Bayesian linear regression. We're going to introduce a concept which is unique to the Bayesian learning or probabilistic learning, which is called predictive distribution. The frequentist approaches are not able to provide predictive distribution. So we're going to explain what's the meaning of predictive distribution. Then we're going to introduce the empirical based framework. Okay, so linear model for regression. So let us start with the simplest model, just linear regression. So I believe everyone has heard of that before, right? So suppose I got D features, right? X1 to XD. Right? We can represent these D features in a D-dimensional vector. We're going to use these D features to predict something, some quantity of interest Y, right? So the linear regression model simply assumes that the prediction, namely the quantity of interest, is a linear combination of these D features plus some bias, right? So the prediction function is represented by some bias parameters W0 plus W1, X1 plus plus WD XD, right? So the parameters include W0, W1 to WD. Right, that's the basic definition of linear regression. However, we know that this model appears to be too simple, right? So how do you guarantee that a simple linear combination of the input features are good enough or expressive enough to predict something you are interested in, right? So you're interested in. So there's a limitation. It only models a linear function of input variables. Right? So a natural idea to extend this, right, to enable nonlinear regression, right, is to perform some feature transformation first. Right? I mean, we still want to preserve this linear model structure, right? Because it is nice as it is easy to derive the posterior distribution of those weights, as we will see later. And it reveals some like additive structure, right? We don't want to break this linear structure, but we also want to model some nonlinear relationship between y and those features x1 to xd. How can we do that? We can introduce some nonlinear basis function, right? So suppose we introduce m nonlinear basis functions, right? We denote them by phi1, phi2, phi3 until phi m, right? So this guy can be viewed as some kind of transformation. You can define whatever transformation over the original feature vector you want. Right? You can do it as a sine function, cosine function, polynomials, logarithm, exponential, whatever you want. Right? It's totally arbitrary. Right? And then our prediction of y is still a linear combination of those basis functions, right? And then plus a bias term, W0. Right? So you can see that in a higher level, right? We still preserve this linear structure, but before we do this linear combination, we first perform some nonlinear transformation over x, right? So overall, the relationship between y and all x values can be highly nonlinear. Does it make sense? Right? That's a very common used trick, right? And also the so-called kernel methods are derived from this kind of idea. And this basis function, yeah, can be any nonlinear function over the input variables. Of course, if you want to still stick to linear modeling, well, you can define the basis function as a linear mapping or linear transformation of the input feature vector x. It doesn't matter, right? So here is some examples. Like, for example, I can define the J's basis function over x as x to the power of g, which is polynomial, right? Or some exponential term, which has a Gaussian form, right? Or some sigmoid function with some shift mu g over the length skew s, right? And if your input feature vector is a vector, right? It's not just a feature value, right? So you might just pick up for each phi g, you just pick up one or several elements of x to construct your feature mapping. For example, I can pick up my gth element for phi j, which is simply xg or sine xg, also on. Again, those concrete examples just tell you that okay, these choices of basis functions are totally flexible. Right? There are no restrictions on that. Right? So this actually gives a very good flexibility. Right? So if you can imagine each phi j as the output of a neural network, it's also doable, right? I can use the neural network to transform my input, right? So imagine the common is neural network, right? The last layer is always a linear combination of outputs from the second last layer, right? So second last layers can each output of the second last layer can be viewed as output for a subneural network, right? So actually this generalized linear model structure subsumes the common used neural networks. This is a really expressive or flexible definition. Any questions so far? Okay, great. Yeah, neural networks can be viewed as nonlinear basis as well. So now we want to, given this model structure, we want to build up some model with probabilistic meanings, right? So suppose this is my model, right? Suppose I have observed the input vectors or feature vectors x and output y, right? So to give some probabilistic meaning, it is natural to assume, okay, the observation y is corrupted by some random Gaussian noise, right? So that we can employ a Gaussian likelihood, right? So basically, I'm assuming observation is t, right? So t is sampled from Gaussian distribution, where the mean is actually your model function, right? And then corrupted by some noise with variance beta inverse. Right? This is a very commonly used structure, right, for continuous observations. So using this Gaussian likelihood, we can do the maximum likelihood estimation, right? So suppose we got n input feature vectors and n outputs, right? Noise outputs, observations, right? When we write down the joint likelihood, we assume their IID, so it is a product of their likelihood of over each individual observations, right? So and here, for convenience, we put the transformation, we put the basis functions all together into a vector. So phi xn, this bolded one, means that the transformed feature vector, right? Or the output vector of the basis function, all the basis functions, right? So that we can write the mean as the inner product between W and this transformed feature vector. And then if we take logarithm of the joint likelihood, we find that the log likelihood has this form, right? It is half n times logarithm beta. Remember, beta is the inverse variance of the Gaussian likelihood, right? And this guy is constant, and then multiplies subtracted by beta times some square error, right? The square error is essentially the summation of the square difference between your observation, each observation, and your prediction, right? And you take half. X and t. X is the feature vector you observed, and t is your observed output. Right? So we didn't use y because y here we assume it is the prediction you make, right? But observation, you always assume there's some random noise. Another question regarding the notation. Everyone is clear? Okay, great. So if we take the gradient of the log likelihood, it will give this form. We won't write down the details. I assume this derivation is straightforward for everyone. Right? Then you set, if you set the gradient to be 0, you want to get the maximum likelihood estimation. You just solve the gradient being 0. It turns out that the maximum likelihood estimation has this following form. So it is a a design matrix phi, transpose phi, inverse phi transpose t. Right? So what is a design matrix phi? This capital phi, right? So it is essentially a stack of the transform feature vector for all the observations. Right? So it is an n by m matrix. N is the number of the training examples. Right? M is number of basis functions. Right? So each row corresponds to the transformed feature vector by the m basis functions. Right? So each row corresponds to one particular example, right? So because you got m basis functions, right? You got, so your transform feature vector is m dimensional. That's why you have m columns. So your whole design matrix is n by m. Does it make sense? We just organize all the transformed features into a matrix, right? Which is n by m. Right? And then by optimizing the likelihood, right? We maximize the likelihood, we got that maximum likelihood estimation of the model parameters W is obtained by take the inverse of the phi transpose phi, the design matrix transpose design matrix, multiply phi transpose T. T is the observed n outputs, right? Is n by 1 vector. Does it make sense? Right? You don't need to try to derive it right now because I'm kind of like skip the details. I believe this is straightforward for everyone. So we don't want to waste too much time on looking at those details. How do we get this, right? So the problem here is that, I mean, from the numerical perspective, P transpose phi is not necessarily positive definite. It's positive semi-definite for sure, right? But it's possibly like low rank, especially for example, so phi transpose phi we know is m by m, right? If you use many basis functions such that the number of basis function m is even bigger than n, we know that this phi transpose phi will be a low rank, right? The rank will be less than or equal to n. So that means the exact inverse of phi transpose phi won't exist. So in this case, how do we compute the inverse, right? We can switch to the so-called Moore-Penrose pseudo-inverse. Right? It's well-defined and well-justified concept, which can be viewed as a generalized inverse operation. But what's the problem? The problem is that if your phi transpose phi is approximately low rank, or the determinant is close to 0, even you can apply this Moore-Penrose pseudo inverse. I mean, it will give you some kind of result, but the values in this inverse will be very large. I mean, the skew, like maybe 10,000, maybe a few hundreds. And as a result, right, we multiply a matrix with a lot of numbers in large skew with something with a vector, right? So you can imagine this W vector, the elements of W vector will be of large skew as well. As a consequence, use this framework, you might fit data very well, right? But we'll switch the data, right, to some test examples. You know, the test example is now changed, right? Then the prediction score with this maximum likelihood estimation of W can get very large, right? It might generate very bad. which leads to the overfeeding. We'll see the concrete example right now. Okay. So we consider using polynomial basis functions, right? Meaning that, okay, I'm gonna do some polynomial transformation of my feature vector. So suppose I only have one feature, right? It's not feature vector, it's just the feature, right? And I can transform my feature to be a vector of m dimensions, right? So I can use x squared to x to the power of m as the basis functions, right? So my regressor will give the prediction as a linear combination of my polynomial basis, right? So a question will be, okay, what is appropriate order m, right? The highest order m shall be used to construct my polynomial basis functions, right? I can use m equals to 0, meaning that I actually use a constant, right? X to the power of m as 0, just 1, right? Or I can use m to be 100. That means you're gonna use very hard polynomials in my regression. And there's a problem, right? How do we select m? How do we choose m? Is everyone on the same page? Okay. So let's see, in a maximal likelihood estimation, right? Suppose I test with different m, and then with that, at most m many polynomials, right? I use maximum likelihood estimation to estimate the model parameters weights, and then I try to fit to the training data and look at how it is match the ground truth, right? So we'll see the performance of using different m, right? So here, let me use this one. The green curve represents the ground truth function, right, which is a sine function, right? And those blue circles are the training data. Now, of course, the training data has been corrupted by some noises, right? So you see, and these red curves are the estimated other curves using maximum likelihood estimation of the weights constructed. Okay. So when m equals to 0, we know that the highest order of the polynomial is just 1, right? Meaning that your regressor function will be a constant, right? So that's why you see this red curve is just parallel to x-axis, right? And when you choose m equals to 1, we know that y equals to w0 plus w1 times x to the power of 1, right? So you see, this is just linear function, and we can see how this linear function is learned to fit the data, right? Of course, in both m equals to 0, m equals to 1, the cases of m equals to 0 and m equals to 1, they kind of underfit the data, and it's far from the ground truth curve, right? Then we use m equals to 3, okay? So when we estimate the model weights with maximal estimation, we can see that, okay, this red curve fits data pretty well and quite close to the ground truth. Now, if we keep increasing m, say, suppose m now equals to 9, and the red curve, which is learned by our maximum likelihood estimation, shows that it 100% fit the training data, right? You can see that it goes through every training point. However, this curve is far from the ground truth, right? It's very different from the ground truth. So this is a typical overfitting behavior, right? So overfitting means that, okay, you fit to the training data very well, meaning that, okay, your training prediction, your prediction error at the training data is very small, but your prediction at some unknown examples, test examples very large, right? If you look at the case where m equals to 9, right? If you can random pick up any examples different from the training set, you can imagine that this test error will be very, very big, right? Obviously, m equals to 3 will end up much better learning result, right? Although the training accuracy won't be 100%, right? However, if you look at the prediction error on any other points, the prediction error will be much smaller than m equals to 9. Okay. So if we look at the numerical values of the estimated all the parameters for all the 4 cases we just no, 4 cases. 4 cases we have discussed, right? So these are the 9 polynomials. Of course, when m equals to 0, we only need to estimate 1 weights, right? M equals to 1, we estimate 2 weights. M equals to, sorry, this would be 3, right? 3, 4 weights, and m equals to 9, all the 10 weights. So we can observe that when m equals to 9, the numerical value estimated for those weights are very, very large. Right? So that means, okay, it can perfectly fit the training examples, right? It can give 0 training error to predict every training output. And the consequence is that, okay, to get such a small training error, you have to make the skew of the weights to be very, very large. Okay? And then if you test your model with a different example, you can imagine this whole very large skews can lead to like observed prediction. Okay? And from numerical perspective, this is essentially the large skews, as we just mentioned, essentially comes from the inverse of this phi transpose phi. Okay? Because phi transpose phi is not necessary to be a positive definite. If the conditioning of this matrix is bad, you take inverse, even you can take the pseudo inverse, the skew of this inverse matrix inverse can be very large, and then end up with the maximum likely estimation W to contain very large elements. Right. We can view the overfitting issue from another common used type of plot, right? In x-axis, we can increase the number of polynomials. That means I'm gonna increase the complexity of my model, right? In the y-axis, I'm gonna examine the error, right? We have 2 types of error. We got a training error, we got test error, right? So from the example we just discussed, right? So you see that when we keep increasing m, our training error keeps going down, right? When you take m equals to 9, your training error goes down to 0. Meanwhile, you have a giant lift of the test error. So it shows overfitting. So now I want to ask, how can we address that problem? Like, how can we avoid overfitting? David. Constrain the scale of the weights. Yeah, that's a good idea, right? So, but how do we constrain that? Yeah, yeah, of course. You can consider, you can construct constraint optimization problem, right? I put some constraint into on W, right? That's definitely sorry, that's definitely a good way of doing this. But here we want to introduce another type of approach, which is called regularization, which you can view it as kind of soft regularization rather than hard regularization. Okay? So if I'm taking our machine entry-level machine learning class before. We talked about this called regularized risk minimization framework, right? But the idea is the same. We want to constrain the weights from growing too big, right? It is because the numerical skills are so big, it's very easy to give very bad generalization error for new examples. Right? In our learning, we hope that the weights are encouraged to decay towards zero, unless the weights shouldn't be zero. This point are supported by data. Otherwise, in other words, it means that okay, if the data says okay, this weight should be non-zero, and we estimate use data-driven method, right? And if data says okay, these weights are not very useful, it should be very, very small, or directly truncate to be zero. So how can we do that? A commonly used trick is called regularization trick, right? So in addition to this square error, right? The frequentist iteration is often called square loss, right? We're going to add a soft regularization term which control the skew of each weight, right? So a very commonly used regularization is just the L2 regularization. So basically, I add into my loss a square norm of the weight, right? W transpose W essentially is the square norm of the weight, right? So that you can imagine, because I want to minimize this guy, right? I want to fit the data as good as possible. But at the same time, I don't want my W to be too large, right? If W to be too large, this part will increase, right? And overall, it will increase the loss. Right? So this gives us some kind of penalty or regularization over the skew of the weights. And lambda here is a hyperparameter, which is called regularization strength. Right? And this is a hyperparameter, so we need to tune them for different applications, so maybe from cross-validation. Hyperparameter. Yeah. Lambda is something you should manually set rather than draw and learn from data. Any other question? Okay. So now, if we use this regularized least square formulation, right? And if we want to minimize this loss, right? And we set the gradient to be zero. This is how we get the optimal W, right? So this is not maximum likelihood estimation at all, right? Because it adds some regularization term and loss, right? So you can see that I'm going to add a diagonal matrix into phi transpose phi, then take inverse, then multiply this phi transpose t, right? So compared to the maximal likelihood estimation, the only difference is that before the inverse, I'm gonna add a small, it's not necessarily small, actually, it's just a diagonal matrix into this phi transpose phi. What's the effect from numerical perspective? Any thought? Any idea? So we know that, okay, if you just look at the phi transpose phi, it is positive semi-definite for sure, right? But it could be low rank. Right? Now, if I add this low rank or positive semi-definite matrix into a diagonal matrix, of course, this lambda must be zero, must be bigger than zero, right? What will happen? Yes, exactly. Right? So we'll add. So first of all, lambda I is positive definite, right? So if you add a positive definite matrix to a positive semi-definite matrix, the summation will be positive definite for sure, right? And its eigenvalue will be at least lambda. Right? And then if your lambda is not too small, right? Lambda, for example, 0.1 or 0.01, if you take inverse, it won't give you like a huge skews. It will make your inverse much easier, right? And give you much reasonable inverse of the matrix. This is from numerical perspective. Does it make sense? Right? So now let's see. We choose different lambda. How and still you use non-polynomials, right? When you choose different regularization strengths lambda, what are the estimated weights? Okay. So first of all, if you choose logarithm lambda equals to minus infinity, it just means lambda equals to 0. Right? So that means you kind of like remove this regularizer, right? You return back to the maximum likelihood estimation. You can see that your estimated weights are very large in scale. However, if you choose a non-zero lambda, right? Even it is pretty small, like lambda equals to e to the power of minus 18. It's very small, right? Your estimate weights, the scale is much smaller, right? At least it's much more reasonable than those guys. Right? If we further increase the value of lambda, say lambda equals to 1, right? This means logarithm lambda equal to 0 means lambda equals to 1. You can see that many weights are kind of truncated, right? It's kind of close to 0. X is some kind of basis selection behavior, right? It means that, okay, maybe this one, or this one are useful bases, right? And for other bases, like, because their values are so small, so it basically means, okay, those bases are not really effective in prediction. Okay. So we can also visualize what are the estimated curve by choosing different regularization strengths lambda, right? So of course, the choice of lambda is also very important, right? So you can see that if you choose lambda equals to e to the power of minus 18, it actually fits the train there pretty well, but it's not overfitting. It gets very close to the ground truth, right? Ground truth curve. However, if you use too large regularization stress, right? Lambda equals to 1, you'll learn function curve is nearly a flat line. Right? Why? Because you kind of truncate many bases, right? You only leave a significant bases like W0 and W1, right? Meaning corresponding to the bias and also the first order polynomial. Okay, so any questions so far? What? Yeah, as we just discussed 9. Right? So look here. Yeah. We consider the cases where you choose big M equals to 9, right? And then you try different regularization strengths lambda and say what are the learned weights. According to those weights, are the learned curve kind of close to the ground truth or not close? Any other question? Usually it's scalar. Lambda is a number. It's 0.1, 0.01, or 1, something like that. It can be a vector. If you want to be a vector, that means, okay, for each element of W, you're going to put a different regularization stress. right? It's still doable, but usually in practice, people will just use one number lambda. Other question? Okay, so we just use one example to showcase how useful if we can introduce some regularization term, right? And this regularization term is just L2 or square of the norm, right? So in general, we can define our regularizer as the power of the absolute value of each grid element, right? The power is Q, right? So different choices of Q value correspond to different type of regularizers. Right? When Q equals to 2, it is the L2 regularization we just discussed. Sometimes it's also called quadratic regularizer. When Q equals to 1, right? So meaning that it's just a summation of the absolute value of each grid element. So this regularizer is called Lasso or L1 regularizer. It's known to encourage sparse estimation of the weights, meaning that it will encourage many elements of W to be 0. And you can even make Q smaller, like Q less than 1, like 0.5, 0.1, and so on, right? In general, smaller Q leads to sparser models, but most commonly used is Q equals to 1 or Q equals to 2. Q equals to 1 is called Lasso. There are many approaches to optimize this guy, right? Optimize the whole loss, right? Q equals to 2 is even easier to optimize, but even for smaller Q values like 0.1, the optimization will become much harder. So far we just talk about point estimation of those weights, right? Maximum likelihood estimation framework, or we add some regularization to avoid some numerical issues and to resist overfeeding, right? So now we're going to talk about the Bayesian framework. How do we infer or apply the linear regression model in the Bayesian scenario, right? So in the Bayesian scenario, as we mentioned, right? So we're going to assume every parameter is a random variable. That means we're going to assign some prior over the model parameters weight, W, right? So the most common used prior is just Gaussian prior. We're going to assign a Gaussian prior over W, where the mean is denoted by M0, covariance denoted by S0, okay? And then given W and the observed training inputs X, we're going to sample the observed training output T through another Gaussian likelihood, right? So phi, again, is a design matrix, right? And W is our weight factor. And here we assume again, we denote the inverse variance of the Gaussian likelihood by beta, right? So because the prior is Gaussian, right? And the likelihood is Gaussian, so it's pretty straightforward to derive the posterior of the weight factor, P of W given T, is also Gaussian. Okay? The Gaussian form is like this, right? We denote the posterior mean by Mn, covariance by Sn. So N, we use this subscript big N to denote, okay, this is the posterior after we have observed big N training examples. Okay? So this is a form, right? Mn and Sn. If you can apply the completing the square approach we discussed before, it's pretty straightforward to derive all this. Right? So I will leave it an exercise for you. So in practice, we won't assume, okay, this S0 is a a dense covariance prior covariance matrix, right? And for convenience, we usually assume that the prior mean is simply 0 vector, And prior covariance is just alpha inverse I. Right? Alpha here is number. This is skew. Right? And then if you apply this general form again with M0 equals to 0 and S0 equals to alpha inverse I, you can immediately get the posterior form, which is much simpler, right? So posterior mean is beta times Sn times phi transpose T, and Sn inverse, the inverse of the covariance matrix, is alpha I plus beta times phi transpose phi. So what's the usage of this, right? And what's what kind of information can we extract by looking at the posterior distribution of those weights, right? So this is very different from the frequentist point of view, right? We only estimate one point estimation of W. Now we got a posterior distribution of the model primes W. Okay? So now we're going to use we're going to observe the information reflected from the posterior distribution of the weights. So for simplicity, we just assume, okay, this is scalar feature X, a scalar output Y, right? So before we observe any data, right, this is our prior, right? So remember our prior is, let me use another color. Our prior is Gaussian prior, and the covariance alpha inverse I, right? So it's isotropic Gaussian, right? So this is how the prior distribution look like, right? We got two weights, like W0 and W1, right? And here, all those figures are kind of a heat map. So the more orange, more yellow one mean larger values, right? The more blue-ish, meaning the values are small, right? Of course, at the center, you have the largest density, right? And when you get center, which is 0 and 0, right? We'll get far away from the center, which meaning far away from the mean, your density is kind of decreasing, right? This is typical behavior of the Gaussian prior density. So we want to look at, okay, before we observe any data points, right? So if we sample W1, W0 from the prior, and then we can construct our fitting function or regressor, right? By using this step y equals W0 plus W1 times X, right? So those red lines show the sampled, show the functions, the regressors constructed from sampled weights from the prior. Right? So you can see that prior is it's kind of wide, right? It's kind of covering a larger span. So that means the range of the W0, W1 sample from prior can be large. Right? And correspondingly, your regressors or your functions on Y is kind of spread it over on the whole plane, right? It can be all kinds of ways to orient it, right? So now let us assume that, okay, we have observed the first data point. So if you look at, if we have a first data point, then we can apply the posterior, the form of the posterior distribution to compute the posterior distribution of W, right? So now the posterior distribution of the weights happened. Okay, so now we can see that the posterior changes a lot, right? So first, it's not isotropic, it's not an isotropic Gaussian anymore. Okay. Why? Because the posterior covariance won't be a diagonal. And you can see the center of the posterior density, which is posterior mean, right? It's getting closer to the ground truth. So here we use a white cross to indicate what is the ground truth value of W0 and W1. So at the beginning in the prior that our posterior mean is at 0, 0, right? It's quite far away from the ground truth W1 and W0, right? But after you have observed one data point, right, you can see that the posterior mean is changed, right? It's not 0 and 0 anymore. It's getting closer to the ground truth, the Y cross. And meanwhile, you can see that the high density region, which you can roughly view them as some lighter region, right, is concentrated much more. Right? So what does it mean? What does it reflect? Exactly. Exactly, right? So at the beginning, like if we haven't observed any data, right? Our part is widespread. It covers a wide region. It means okay, we believe that there's all kinds of possibilities about choices of W0 and W1, right? And then when we observe one data point, right? When we integrate this information into our posterior, we immediately shrink our uncertainty about the W1, W0 values. The posterior formula means okay, your high density region is shrink large. At the same time, the posterior mean is getting toward to the ground truth. And this point can also be reflected by looking at the sample, the regressors, right? Again, from this posterior distribution of W0 and W1, we can sample W0 and W1, right? Because now the high density region is much more smaller, right? Much smaller. So you can imagine like, okay, your sample W0 and W1 are kind of closer to each other as compared with the prior case, right? And then you construct the regressor, meaning this linear function, those lines are much closer than before. And if we and this column just to show the likelihood function, right? X is your observation, X and Y is your observation, right? And again, this Y cross is the ground truth. And when you vary different W0 and W1, you will get different likelihood values, right? And ideally, we would expect that when you W0 and W1 is at the ground truth, right, you get maximum likelihood, but it's not true. The reason is that the data has some noises. Right? There are some noises, and you won't be guaranteed to be maximum. So let us receive the next data point, right? Suppose we have observed the two data points. Right? Again, we can apply the formula to compute the posterior distribution of our weights, right? So if we look at the posterior distribution of our weights, what can we observe? The distribution get even more concentrated, right? So if you look at the high density region, right, it's shrinking to this small circle, right? As compared with the first data point, right? Behind this region is still much larger, right? Since this inclined ellipsis, right? But now after you have up, sorry, two data points, your posterior distribution is further contracted, right? At the same time, your posterior mean is getting even closer to the ground truth, right? That means, okay, I have observed, I have integrated more data information, so my estimation is getting even better. At the same time, my uncertainty about those model parameters W0, W1 is further reduced. Does it make sense? And if we use this posterior to sample W0 and W1 and draw the regressor curves, right, you can see that those lines are getting even closer. Right? Why? Because the high density region is further reduced, right? So you can imagine many samples W0 and W1 are getting even closer. So the lines, the corresponding lines here, are getting closer and closer, right? By the way, this blue circle is just the training points, right? So if we keep doing this, suppose we get 20 points, right? We have observed 20 points. When we compute the posterior distribution, you can see that it kind of like contracted into a very, very small area, right? And your posterior mean is still close to the ground truth, but does not overlap. Part of the reason is that because your data contains noises, it won't guarantee that your estimation will be exactly the same as the ground truth, right? But your uncertainty is very, very small. And if you use this posterior to sample W0 and W1 to construct the curves, like y equals W0, W1x, right? You can see that because W0 and W1, different samples might only differ a little bit. So when you draw those curves, they kind of largely overlap. Does it make sense? Any question regarding understanding of these figures? It's not Gaussian. It's not Gaussian. Oh, actually, it's yeah, you can view it as a Gaussian, but there's a structure inside the Gaussian, right? So if you write it, it should be something like this, right? Should be y W0 plus W1 and some noise level, right? Something like this. So this figure just shows, okay, when you use different values of W0 and W1, given X and Y, how this likelihood changes. Right? So you can see that different point on those panel indicates different choice of W0 and W1 values, right? And here X and Y are fixed. They're just observations. They observe input, they observe output. Of course, we have different weights. Your likelihood, which is discussion likelihood, has different values, right? And ideally, we want that, okay, this value is maximum, achieves maximum when W0 and W1 are the ground truth, which is Y cross. However, because Y is kind of corrupted by some noises, it won't guarantee to be maximum when W0 and W1 are the ground truth. But if you're close to the ground truth, you still got high likelihood. Any other question? Yeah, hopefully this figure can give you some kind of sense of flavor about the Bayesian view, about modeling, about inference, about observation. You know, it's different from, okay, I just look at one point. Right? So the posterior distribution not only reflect how close you're approaching to the ground truth, but also reflect my uncertainty. if we extend to the general regularization, right? So we mentioned that here in the regularization, we can choose different values of Q. Q equals to 1, Q equals to 2, correspond different regularization, right? If we want to extend it to a Bayesian model, we can apply a prior over W, which is consistent with those different regularization, right? So this guy is just the normalization factor, right, to ensure that this is a valid distribution. And this one is actually corresponding to the regularizer, right? So when Q equals to 1, which corresponds to the L1 regularization, this prior is called Laplace prior. When Q equals to 2, you see that this is essentially a Gaussian prior. Okay? For Gaussian prior, it is very easy to derive the closed form of the posterior distribution of the weights, right? But for the Laplace prior, no closed form of the posterior of the weights. So if you want to do some kind of similar analysis of this, well, we have the estimate posterior, you have the approximate posterior, say by Markov chain Monte Carlo sampling or other approximate inference technique. Okay, next we're going to introduce another thing which is unique in Bayesian learning, which is different from the frequentist approach, which is called predictive distribution. So what is predictive distribution, right? So we know that in a Bayesian model framework, right, given data, right, we in principle will have some posterior distribution of the model parameters W, also given this hyperparameter alpha and beta, right? So that means in the prediction stage, right, given some new test input, right, if you want to predict with your model parameters, you actually have many choices of W, right? It's not necessary to be just one maximal likely estimation of W, right? You have many choices, right? So a natural idea would be, okay, why not we just leverage all possible values of W, right? We're gonna integrate them together to make a much more robust prediction. Right? This leads to the predictive distribution. So what is predictive distribution? I'm gonna construct a distribution of the prediction given the data only. So here the bold T are the training data, and the unbold T, the skill T, the Italian T, is the prediction. Right? So I'm gonna marginalize out the model parameters W according to its posterior distribution. How can I marginalize out? Right? So I'm just do this integration, right? So in this integral, we know that for a particular W, the distribution of the prediction T is this guy, right? P of T given W and beta. Beta is the inverse noise variance of the Gaussian likelihood, right? And then we're gonna consider the distribution of W, right? So because we have observed data T, so we got a posterior distribution of W given the training data is bolded T, right? Given alpha and beta just prior inverse variance, beta is just likelihood inverse variance, right? So it's here and here, right? And then in a regression case, right, in a linear regression case, we know that the distribution of the prediction given the model parameters is a Gaussian, right? We know the predicted distribution of the W given the training data is Gaussian, right? When you marginalize them together, which is called convolution, right? It's called convolution and it has an analytical form. It turns out to be another Gaussian, right? So it gives us the result that the predicted distribution of any test example given the training data only with model parameters marginalized out is another Gaussian distribution. And Mn and Mn is the same as the we defined before, Mn here, right? And the variance is computed in this way. Again, I'm not gonna show this how this derived. It's pretty straightforward. If you can use the completing the least square approach we discussed before. So now I want to observe how the predicted distribution varies along with more and more training data. So again, this green curve is the ground truth, and the red curve is the learned curve by using the learned curve of this mean of the predictive distribution. So, and this region, this shaded region, is just one standard deviation, meaning that, okay, this part is the posterior mean of the predicted distribution plus one standard deviation of the predicted distribution. Right? This guy is just a mean minus the one standard deviation. Right? So from this, we can not only see, okay, what kind of curve you have estimated so far, but also what is the uncertainty at different inputs, right? Does it make sense? Right? So at the beginning, if we only observe one data point, right? So you can see that your mean of your predicted distribution is kind of like a flat line, right? It's far away from the ground truth, and also at the places where it's close. Not gonna use close to the observation, your variance, the predictive variance is relatively small, right? But when it's getting far away from the training data, you can see that the predictive variance are getting much larger. Meaning that, okay, the current model trained with only one observation is quite uncertain about places where you're far from the training examples. Does that make sense? Next, if we add one more data point, right? It's here. You can see that at one more data points, it can make the learn curve better, right? It's still kind of far away from the ground truth, but your predictive mean activates to be a curve rather than a flat line, right? It's getting closer. And again, we can see that surrounding the training region, right? Meaning here and here, your posterior, the predictive variance is relatively small, meaning that, okay, you're less uncertain about your prediction at those regions. However, when you get far away from the training points, your uncertainty becomes larger again, right? So if we keep adding the data points, right, you see that your predictive mean in a predictive distribution, right, is getting closer and closer to the ground truth. At the same time, your uncertainty about the prediction at different places are shrunk as well, right? So if you have observed many data points right here, so you can see that your the mean of your predictive distribution is getting much closer to the ground truth, right? At the same time, your uncertainty everywhere is reduced to a reasonable range. That's how this that's what the last figure shows. Any questions so far? Is everyone comfortable with this? Okay. We can also observe how our estimation, when you incorporate more and more training examples, right? The posterior distribution, the predicted distribution, what kind of things the predicted distribution can reflect, right? So if you look at the posterior of the weights, right? And then if you sample those weights, you can construct the curve, right? So in our model here, we use a Gaussian basis functions, right? A linear combination of Gaussian basis functions. So that means your sampled curve won't be a line, right? So at the beginning, if you only have one data point, so you can imagine your posterior distribution of the weights are kind of wide, right? There are still many uncertainties about the values of W. So then if you sample weights from your current posterior, and then construct your curve, right? This guy should be something like that, right? 9 and WJ and phi J X, right? So this guy is Gaussian basis, right? And because W, the posterior of W, given only one data point, is still wide. So the sample W will be scattered, right? Will be scattered, and then the corresponding curve are kind of like wild, right? And then after you observe two data points, we know that the posterior distribution is get some contraction, right? It's contracted. And then your samples of the W will be closer than the previous case where you only see one example, right? And the curves are getting closer as well. If you keep observing more and more data points, integrate them into the posterior distribution, then the samples of the W eventually will all be very close, right? Or there are only minor difference between them. And then if you construct your curve, right? And then they will get much, much closer. Any questions so far? Is everyone comfortable with this? If I have never done Bayesian stuff, like those kind of figures or things might be you might feel not that comfortable to look at those figures. But this do reveal the flavor of Bayesian stuff. The point is that, okay, by incorporating more and more data points, our estimation of the model parameters is getting more and more accurate. At the same time, we kind of reduce our uncertainty because we always deal with the distribution rather than just some points. Okay. Okay, I think let's stop here today. Next, we're going to talk about a Bayesian model comparison, namely how do you select those hyperparameters, including alpha and beta, we just discussed in our formulation.